So, guys, first of all, thank you for coming. This is, full house here, not a single seat open. That's pretty awesome. So, first a question: how many of you have actually done natural language processing or sentiment analysis? Okay, well, quite a few. What tools do you use? NLTK, NLTKs, text blob. Yeah, text blob is easy, nice and easy. What else? What else? GenSim. Okay, so we'll have some GenSim here. Any other tools? No. Yep. Okay. So that's a Java one, right? Yeah. Uh, okay. Gotcha. Okay. Cool. So yeah, the NLTK package is probably the biggest beast in the room. Yeah. So the microphone only goes to the camera. I think. Yeah. I will have to project. Yeah, so we're going to use a variety of tools. So we're going to use GenSim and Word2Vec in today's tutorial, and then I'm going to actually show you a way to do it without having any of the fancy neural network tools, using NetworkX. Have anybody used NetworkX in the past? Yeah, cool. Yeah, so NetworkX is it's really designed for social network analysis and graph mining, but I've adapted it to work on sentiment analysis. And frankly, you don't even need NetworkX to do what I did sort of in the final portion of the tutorial. You can roll your own. So let's say you're in a classified environment. Anybody here works in a SCIF? Classified data? Nope. Okay, my wife had this problem. She works with government data, and she was not allowed to have access to anything other than the Python standard library. And then they say, hey, you need to do sentiment analysis. And yeah, it was fun. I'm trying. Yeah, so this mic is for video only, and it's actually not tied into a PA system. So yeah, I'm also trying to get over a cold. So if I start speaking like the Godfather by the end of the day, anyway, so let's start with what is emotion mining. So our sort of standard sort of run-of-the-mill sentiment analysis. This is what you get in text blob, and this is what you get in sort of off-the-shelf algorithms. So this is so-called bag of words approach. So oh wow, this really is cut off. Yeah. So what we do? Yeah. I already did. Yeah, it's an aspects ratio problem actually. But what bag of words approach does is we have a list of good words versus bad words, and we had a number of those lists. The most famous one, people took a few thousand movie reviews off of IMDb. I think it was 700 good ones and 700 bad ones. So you look at the star rating, people that rated movies 10 out of 10 and 1 out of 10. So you take some really good reviews, some really bad reviews, and you create a lexicon. Those words such and such constitute good, words such and such constitute bad, and then you just look at the ratio of good versus bad in a sentence. And it's real simple. You can if you have that lexicon, which you now can download more or less anywhere. If you have that lexicon, you can create your own sentiment analysis tool in about 15 minutes using nothing but standard library. It has one big problem, and the problem is it absolutely is terrible at recognizing nuances of human language. And this is my favorite. I used to evaluate sentiment analysis algorithms for clients. This is my favorite test I run. Yeah, this is the. Yeah, if this comes out as a highly positive sentiment, I would throw out the algorithm immediately, and most of them did not make the cut. Now, we actually have a slight problem with this, as far as human language is concerned. What we don't have an algorithm problem here. We have a language understanding problem. So if we take, there was actually an experiment done at Stanford where they recruited several hundred students to go and read short passages and score them on the -1 to 1 sentiment scale. And the people, so humans who are supposed to be the gold standard, they only agreed with each other 85% of the time. So that our gold standard of having, an English major who is well trained in deciphering the meaning behind the passage or whatnot. Even our gold standard is only about 85% good. And here we're trying to get a dumb computer to do it. And one of the problems there, the students that were recruited to do this, they kept writing comments like, "This is stupid. I cannot tell you if this passage is good or bad, because it has some good and some bad and some terrible and some amazing and some disgusting. And how do I squish that whole rich layer of meaning into -1 to 1?" And this is actually one of the biggest failures of sentiment analysis to begin with, that you're trying to take something that's rich and poetic and squeeze it into -1 to 1. So then we do something that's a little bit more advanced. So we can now decompose the English language into lexical trees. So we break it up into noun phrases, verb phrases. We can figure out when there is a negation. And by the way, the word "fucking" in the flat tire problem, in this case, acts as a negation, but sometimes it acts as an amplifier. So try to figure that one out. But the main problem with this is English is actually lexically ambiguous. So this is the thing I throw at those kind of algorithms. By the way, so buffalo, 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 buffalo is actually a perfectly grammatically correct English phrase. Yep. In fact, the original phrase, so this is a short version. The original phrase, I think, is 8 buffaloes in a row. It goes from the fact that buffalo has 3 different meanings in the English language. One is the animal. The other one is a city in upstate New York. And the third one, which people actually forget, is a verb which is a synonym of to bully. So, if I buffalo somebody, I guess I'm butting heads with them or something. So buffalo, 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 buffalo is... Yes, yeah, you got it. Yep, so an animal from buffalo is bullying another animal from buffalo. And, toss that at a lexical analyzer and see what it gives you. And, you'll have fun with it. So emotions are complex. And this is probably the biggest thing I learned while doing this for a number of different clients, number of different industries. I've done this in healthcare. I've done this in advertising. I've had to build an emotion classifier. This was kind of crazy project for a feminist, sex-positive blog and magazine. And the biggest problem was that, so I needed to filter their incoming user-generated content and distinguishing between sex-positive feminist content and porn is extremely hard. And by the way, try to sit in a public place like a coffee shop and work on that project. All I can say is thank God for text-only web browsers. Thank you, links. But actually, we were able to figure out that more or less the same emotion, the same, I guess, actions were described very differently in the feminist content versus, I guess, male chauvinist content. So that ended up being actually a perfect thing for a support vector machine. So, oh, this. Okay, so and then so I was playing with all of this stuff, and then this movie comes out, Inside Out, and anybody here has kids? Yeah, so you've probably seen it at least 28 times or something like that. So you're watching this movie, and I was sitting watching it with my son. And I realized that I remember something like this from my psychology classes back in my undergrad. So I actually went to dig, and I realized that it is actually a very sound explanation of how psychologists understand human emotion. That movie is a lot deeper than it seems. So, so I started thinking about how can we create a more nuanced sentiment analysis tool that would actually perform like the characters in that movie in one way or another. So if you remember, so when it starts out, when the main heroine, when she's little, all of her emotions are simple. They're yellow, green, red, blue. They're colored one way. And as she grows up, she learns that the emotions can be complex. So you could have something that's bittersweet, or you could have something that starts out angry and then quiets down, or something like this. And so you end up with more complex emotional content. And that's really what I wanted to get to. So I built a few versions of that. I'll show you a couple ways I approached it. I'm not going to give you one prescription. I'm going to show you a few different approaches. One of the main problems right now with this is we don't have enough human-coded data with high-quality emotional markup. So, if you by chance teach like an English composition class with 150 students, you're in a good place to generate some data. Just give them homework. My cousin teaches linguistics 101 at Rutgers, so I called her. I sent her some text corpus, and hopefully at the end of the semester, that's going to be one of their homeworks to bring me human marked up texts with better emotional content. So now this actually gets a little bit more interesting. And oh shoot, this really got cut off. So the five basic emotions, that is actually only our only one view on how we see this, and there is a number of others. So, for example, Georgia Ascoli, whose name got cut off over there, he's a professor at George Mason. He's actually a neuroscientist, and he conducted an experiment where he started putting people into an fMRI machine and reading passages to them, and have them score. And I think he originally started with 19 different dimensions, what came out after he did principal component analysis on the resultant data, what they found is the most salient dimensions, the ones that cause the most activations in the human brain. So he cut it down to 9, and of which the 4 are more important. So one is good and good versus bad. So that and that's actually a sliding axis. So you can make it -1 to 1 if you like. So that's going to be our normal sentiment. Then there is calm versus excited. So arousal, something that really increases the level of your neuronal activity versus not. So there is a strange one that's open versus closed. And that one was really difficult to describe as, but it really stands for: do you have a choice in this matter? Is this something that is happening to you, or is this something that you can change? And the last one was simple versus complex. So that one is actually very interesting. There is another data set out there. Has anyone gone on a date with through OkCupid? No. Okay. So the best thing about OkCupid is not the fact that it's a dating site. I've been married for 10 years. I have no idea what dating sites look like. So it's the interesting thing there is you can there is this crowdsourced question and answer mechanism, and one of the questions people ask when they're looking for a date is, are we compatible politically? Never go out with a Trump voter. But not everybody is comfortable actually asking that question up front. And other people have asked all kinds of other questions. So the founders of OkCupid, they ran a correlation study looking at what questions seem to correlate more with being politically conservative versus liberal. And the highest correlation was asking people, do you prefer your life to be simple or complex? And liberals tend to go towards complexity, while conservatives tend to go towards simplicity. And that was the highest correlation. So if you want to go more in depth, there is a book called Dataclysm. And that's basically, it's built out of a collection of blog posts, and it's all based on about 5 years worth of data coming off of OkCupid. So McGraw is an interesting guy. So anybody heard of this comedian Yakov Smirnov? Yeah, in Soviet Russia, the sentiment minds you. I just had to use this. I have a real Russian accent, right? So Yakov Smirnov, with the fall of Soviet Russia, Yakov Smirnov stand-up comedy career sort of plummeted, but he still has his club. But he works with a professor of English and linguistics, so McGraw, like the first name, at Washington University of St. Louis, and they have created a program in humor studies. In St. Louis, humor studies, you. Sorry, no more. They came up with a theory of what makes things funny. And it's a theory of benign violation. So it's the idea that your expectations are violated in such a way that so on one hand, it's something that might possibly hurt you, but you also definitely know that it will not. And there is think about, if you think about yourself falling off the roof, that's pretty terrible. You will never find that idea funny. But if you watch Charlie Chaplin falling off the roof, or I don't know, Roadrunner is chasing the coyote and he falls off a cliff, that's funny. Because so it's a violation because you are about to impact the ground at 9.6 meters per second square. But at the same time, it's benign because Charlie Chaplin walked away from it, and the Roadrunner always survives. So so then it's funny when Roadrunner gets squished. Very similar idea though. So you now shift into dimensions of good versus bad. That stays, but now or later, or maybe in the past, or certain versus uncertain. So that actually parallels the open versus closed in the Ascoli work, and close versus far. And that one is not so much physical distance, although that also works, but it's your interpersonal distance. So is it happening to somebody who is very much like you, or is it happening to the Roadrunner who is definitely not like you? And what happens is so we can find positions in that vector space. So think of all of those things as different options to represent emotion as a vector. So one has 5 numbers, the other one has 4. You can build your own. You can build your own theory, and if you start watching, my favorite thing for a while was watching commercials and scoring them on this vector scale. So rush to your Honda dealer now, or you will miss amazing savings. So they're trying to tell you that it's now and that it's you, but the problem is the threat, the bad things that will happen. You miss an amazing savings. That's not so bad. So it's not connecting. I'm not about to go rush to a Honda dealer, but at the same time, if I get a phone call from my wife saying that, I don't know, FBI is knocking on the door and they have a search warrant, so it comes from somebody close to me, it's a bad thing that is happening now and it's definite. I'm going to act on this. I'm going to hit the road. And of course, if it happens to be April 1st, then I'll be like, yeah, right. So in this case, that violation becomes benign, and then I might find it funny. I actually did this to my wife. I bought a mouse. She's very afraid of mice. I bought a mouse for $1 at the pet store and took a picture, put it on Facebook, and I was like, guys, watch it. 30 seconds. I will be divorced in 30 seconds. 1, 2, 3. 28 and a half seconds, I'm getting a call. My phone rings. I'm calling my lawyer. Anyway, I'm still married. She tolerated that one. But the idea here is you can generate your own context. The one that, so it could be an inside out, just looking at basic emotions, or you could build your own set of context, and then you can build a classifier to mine and to create vectors based on this context from text. And that's what we are going to build today. So I'm going to use sort of a mongrel model, and I lost my screen. There we go. No? Okay. So I'm going to build a mongrel model that has a little bit of traditional sentiment. So it still does positive, negative. But it doesn't actually do it in an exclusive fashion. So something could be a little bit negative and a little bit positive. And then on top of that, we'll build a more nuanced emotion model. And I'm going to show you a couple of ways you can do this. And then we're going to build a completely free-form graph-based model that you can initialize with really any context you can think of. All you need is some initial data to build this context. Well, so to give you an example, one of the things I've done with that model was looking at Republican primary candidates, and I would pull. I just loaded up their speeches into the model, and then I would look at how similar they are to each other. So is Trump more like Romney, more like? Well, actually, Trump was not like anybody else. So. Yeah, one of the things I wanted to do for are you sure you guys want to do this? I don't want anybody falling asleep. Somebody bumped that switch.
We all have a comforting glow with our laptop.
Yes, everybody is getting the laptop tab. Nope. Nope. Okay. Is there a button that releases the tiger? So yeah, it's the unmarked button, right? So okay. So let's move forward. Yeah. So you can make your own theory. Well, so things you could do is you could look at press bias, for example. Load up different stories from different press outlets and see if they describe the same thing in the same way or different. You could look at two sides to a conflict and see how different press outlets stack up against it. Stuff like this. So it's actually a pretty powerful tool. So yeah, so typical sentiment. It's usually a bag of words approach. We're still gonna stay with bag of words, but we're gonna make it a little bit nicer. So sort of an improvement on the basic sentiment that's built in the support vector machine, and classifying. So you vectorize text, and then you classify it based on good versus bad. So we'll walk through how you vectorize and should be able to put together a quickie support vector machine on this. It's actually not really good. So for support vector machines, I've only gotten accuracy of about 65% on this. And remember, humans are 85, so humans are not very good. Yeah.
When you just do bag of words, like I'm assuming there's some basic preprocessing, stemming.
Yes, we're gonna go through that. Yeah. So I do stemming. I clean up everything. Take out all of the characters that are not necessarily belonging to text. I usually do language detection, and I drop everything that's not English and Spanish, unless I've been asked to specifically work in a specific language, and that's largely because the stemmers don't work all that well, or you have to have a specialized stemmer for every language. And English and Spanish, the stemmers are really stable. Other languages have no stems. So Arabic is one of the. Actually, Arabic and Hebrew Semitic languages, they have a very different construction, where you take a root. I know Hebrew better than Arabic. In Hebrew, there is a 3-letter root that's always a verb. And from there, you apply a set of finite transformations. It's actually very mathematical to derive different meanings. Some of those transformations are adding prefixes and suffixes, and some of them are actually changing the vowels inside. But they're all describable mathematically. It's pretty cool. But it's a completely different model from what English does. So,
Are the unitary operations going to reverse?
yeah. Yeah, so Hebrew and Arabic are they're completely different animals. Chinese and Japanese, they're also completely different. The Korean actually Korean is interesting because Korean has very distinct rules of how the characters are constructed. So I have never worked in it, but I have a friend who is Korean, and he's working on basically deconstructing Korean linguistics. It's pretty cool, but I don't know Korean, so let's see. So okay, so we need to start with data sets, and data sets it's largely garbage in, garbage out. So for this tutorial, I thought what I was going to do is go to Facebook and grab every pro-Trump Facebook group and every pro-Hillary Facebook group, and then try to filter the posts based on whether they. So if I'm looking at Trump, I would take posts that only mention Hillary and posts that only mention Trump. So pro-Trump mentioning Trump, pro-Trump mentioning Hillary, pro-Hillary mentioning Hillary, pro-Hillary mentioning Trump. I thought that was going to yield me some good data. Wrong. You can have the data. I'll put it up on probably on Dropbox. It's a pretty sizable file, a couple gigs. You can have the data. You can do what you want with it. It's garbage. So I'm not actually going to use this. And of course, I only found out last week that it's garbage. And the problem is, one could predict how, just by watching sort of the tenor of this campaign, one could predict how people are feeling. But when you actually start looking at the texts are by far not as one-dimensional. So it's a good target for testing the classifiers. It's a bad data set for building the classifiers. For building the classifiers, you want something cleaner. So I went back to the gold standard. And the gold standard is still the IMDb movie reviews. So that text has been cleaned. IMDb actually does not allow any special characters or HTML in their movie reviews. So that's nice. And we also have the star rating for the movies. So that's even better. So if it only takes the 10-star reviews and takes the 1-star reviews, we're gonna get pretty good data. And then there is another data set called the NRC Emotion Lexicon, and so that one was actually hand built, and it has listing of words by the inside out style emotions. So we're using that one. So my first attempt was to build an ensemble classifier, and that would be just a bunch of support vector machines, one trained for each emotion, and run them together. And what I found is some emotions, anger and joy, work pretty nicely. Other emotions, they got completely confused. So I ended up scrapping that. And where I went from there is building a word-to-vec model, and that's what I really want to talk about. I'm sorry. So word-to-vec is it's actually a pre-built neural network. It does not use tools like TF-Learn. Word2Vec is a pre-built neural network for NLP, and it does a very interesting job at reducing the dimensionality of language. So okay, is anybody familiar with text vectorization? Okay, so sorry, you'll be bored for a few minutes. So I just want to talk through this. Okay, let's need to change my resolution back. So we're gonna do, yeah, okay, so yeah, so I'm just gonna go. And yeah, okay, we're here. So I'm gonna just start by loading some movie reviews, and I've done a couple of things here. So that's and by the way, I will post all of the code on GitHub. So so this loading function, it takes text from a text file, it splits it by sentences, so just using period, and it converts everything to lowercase and cleans off any kind of special characters that could be there. And I don't want to spend too much time going over it. It's just a bunch of regular expressions. Yeah. Okay, let me try this. This is all I get. Oh, actually, hold on. See, 1280. No, nope. Still cutting off. Well, it's a little bit better, no? No. Okay. Yep. Okay. Well, I guess I'm gonna do this. Right. Better. Okay. That should be readable. Okay. So we loaded up the data. So movie reviews is just a list of text. So yeah, you I think, yeah, I like it. Effective but too tepid biopic. So you're getting the idea of how people express emotions. Yeah, so and where I like this. So we have about 10,000 sentences here, and some are long and some are short, but all of them have some emotional nugget in them, which is pretty nice. So the next thing we need to do is convert those sentences to vectors, and we are going to do that. And again, this is a helper function that I will give you. Request. I need to switch windows here. There we go. So this process function that's where the stemming happens. So first thing we do is we detect language. So that uses actually Google language detector. By the way, does anybody know how language detection works?
By the
Trigrams, right? Yeah. Okay. Can I tell the others? Okay. Okay. So language detection it's actually really cool. And so you imagine you take text from Wikipedia, and you take 3-letter groupings, so trigrams, you just run a sliding window across the entire text of Wikipedia in all 147 languages, and you compute frequencies of trigrams. Now, you take any random text. So it turns out that every language has its own trigram signature. So anybody wants to guess what the most common trigram signature is in English? Huh? T-H-E. T-H-E. No. So so every language has its own signature, and then it becomes trivial to build a classifier that takes any random piece of language, runs the same sliding window, looks at the trigram frequencies, and guesses what language it's in, and it's remarkably accurate. So. So I'm just going to show you. Oh. Yeah, it's as simple as that. And well, actually, let me see what it does with Unicode. I'm going to switch to Russian. Oh, Bulgarian. Well, close enough. But they're both Cyrillic languages, and that was sort of mildly obscene. Like that was basically like WTF, but in a milder version. Let's see if I can. Let's see if it will distinguish between Russian and Bulgarian. Yeah, okay. So a little more text, and it actually will distinguish between Russian and Bulgarian, even though both use Cyrillic alphabet and are very similar. Yeah.
Is this are you doing this work in 2.7 or 3?
2.7.
Okay.
Yeah, that's why Unicode. Yes.
Okay.
Yeah, it's not Unicode by default. Yeah, so by the way, one of the reasons I'm still not using 3 is not all of the packages that I use are supported. It's getting close. I will switch very soon, but
I was gonna say because I'm also at 2.7, but dealing with Unicode stuff sometimes makes you exactly.
I will show you a magic package.
Okay.
You're gonna love this. The package is called Unidecode. Not Unicode, Unidecode. So I'm going to do. So check this out. I'm just gonna paste this. So paste. So I'm putting in a string in Russian, and it will transliterate it into Latin alphabet and return a plain Python string. And in general, it does a really good job. The only place where it gets confused is Chinese versus Japanese. And that's really because the characters are very similar. Actually, there's the same characters. So hold on. So let me get some Chinese text. Chinese Wikipedia, maybe? So, okay, I'm just going to cut and paste line of Chinese. Okay, and so anybody speaks Chinese here? Okay, tell me. So, first of all, what does this say? Okay. 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 So yeah. Oh. Oh. Yep. I forgot the U. Let's see. Is this any good? Yeah. Cool. There we go. Your Unicode problem has been solved.
Yeah.
Yep. Yeah, so the only problem is it does confuse Chinese and Japanese. And there are very different languages that use the same character set. Everything else works pretty well. So yeah, when I work with foreign languages, I often use this just because it makes it a little bit more comprehensible. I don't read Arabic, for example, and I read Hebrew so badly that I might as well not read Hebrew. 5 years of Hebrew school when I was a kid, gone to waste. Okay. So the next thing, we start by the text and language. Then, I'm using the tokenizer from an LTK, simply because it's a little bit more robust. You can write your own. So your simplest tokenizer is going to be just splitting on spaces. But an LTK one does a little bit better because it also strips out periods, it strips out punctuation, does a lot of stuff like this. Then we also load up a stop list. So stop lists are words that you don't want to use or don't want to be taken account of. And this is one I downloaded off of one of the sites. Feel free to edit this. But yeah, mostly so for example, I should probably take some words out of this. So like the word like and liked. But was there best? Yeah. So for sentiment, you should edit those things and not use. But your simplest stop list is going to be just taking out the in, out, etc. Because those words get used a lot, and it's going to throw off TF-IDF, term frequency measurement. And I have another one for Spanish. And that one just gets cut on the column. So this one is a lot more a lot smaller and doesn't have as ambiguous words as the English one. But again, stop lists, there's a lot of them to go. There's a lot of them floating around. Just grab one and edit to take out the words that you don't like. Put in words sometimes words creep in, so you can put them in. So the next thing we do is we stem it. So Snowball Stammer is sort of a standard LTK stemmer, and let me just show you how this thing works. Oh, I need to import first. Grab movie reviews. Okay, so okay, there we go. There's an Arnold Schwarzenegger movie, and so what we're doing here is we're running this. We're going to run this sentence through this function, and it's going to go through all of the tokens, and just take the stem. Actually, stem. According. So what stem does is it basically cuts off prefixes and suffixes to bring a word to canonical form. So if it's a plural, it's going to cut off the plural. If it's gerund form, so the ing form of a verb, it's going to cut that off. And the idea here is we want our linguistics to lock up. We're disregarding the grammar, we're disregarding tenses, we're disregarding a lot of things here. So we need to lock them in on the stems. And that is the easiest way to do this. So I'm going to process movie reviews. Okay, so this is what happened after we applied the stop list, and sorry. Yeah, yeah. Oh, yes. The er is yes. That's a suffix. He Schwarzeneggs. Ooh, I like that. We need to verb it. To Schwarzenegg. Yeah, I've been Schwarzenegging all day at the gym. That works. Yes, go ahead. I stick with stemming partially because lemmatizing is slower, a lot, and it doesn't matter when you're doing 10,000 articles or not so much. The moment you get into hundreds of thousands, there is a whole bunch of algorithms that are really good in an LTK, but that are also really slow. Well, by the way, so one thing that I've been asked, why don't I use Lowenstein distance, or Levenstein distance, sorry, instead of stemming? Because and speed is the only issue. Levenstein is so slow that you cannot on a non-trivial data set you cannot use it. And I've spent months trying to work around it, and I gave up. I started building indices, did a completely different thing just to get rid of Levenstein distance. Okay, so this is more or less our pre-processing. So we're going to we're just going to take every sentence in movie reviews and process it. Takes a little bit of time. So here you can see that's 10,000 sentences or so. It's going to take about 20 seconds, maybe a little longer. It will happen eventually. Come on, seriously. So the next thing we're going to look at is we're going to look at word frequency. And the reason, so a lot of algorithms, we can actually stop right there. We can just do word frequency analysis. For us, it's going to be actually a pruning step. So what I'm going to do is create a word frequency counter across that entire data set. That's actually very quick. And yeah, so that's going to give us frequencies of all kinds of words. I'm wondering what's going to be most common. Most common, say, 20. Film, movie, make, story, time, characters, good, comedy. Yeah, makes sense, right? Those are the most common words in movie reviews. Also, I just want to show you a quick observation here. The numbers, you see how the frequencies drop off sharply? So the most frequent is 1805, and the 10th most frequent is in the 300 range. What we have here is actually power law distribution. So it's a very sharp drop off. And we're also going to have a lot of words that only have been used once. So I'm going to single sentence. And see if we yeah, so all of those words have been used only once. There are 5,300 words used once out of total 12,000 words. So a little bit less than half. And we're going to drop them. So here I'm going to go through. I'm going to go through all of the tokens that we've generated in the previous step, and I'm going to drop words from those texts that have only been used once in the entire corpus. So remember that movie review about Schwarzenegger? That one is actually okay, but yeah, they basically those texts start getting a lot shorter. And we're finally going to start creating a vector model. So right now we're using words, and machine learning algorithms generally don't like words; they like numbers. So in the simplest thing we're going to do is we're going to create this dictionary, and so all this dictionary does is it gives a sequential number to every word that it sees, and it creates a backwards inverse index. So dictionary 1430 is simple. So now if we take a sentence, we can vectorize that sentence. So we are converting it from a sequence of words or sequence of tokens to a sequence of numbers. So now we are going. So now I'm going to create a corpus. So now I'm going to go through all of the text, and I'm going to convert all of the words to numbers. Corpus. Yeah, you're right. Yep. Yeah, I'm used to everything becoming an object at some point. Yep, there we go. So now, this is kind of funny, actually. Here, so you see the first sentence in the corpus is actually movie. So we're still preserving the so movie review 1 has been transformed into that. And that's just a list of tokens that and the IDs have been assigned sequentially, so so that's when it starts. Let's see, I'm gonna do this. Yep. So those are no longer sequential. Okay. Corpora. There is another model we can build, and it's called the TF-IDF. So anybody familiar with TF-IDF models? Yeah. Okay, so that a lot more people are. So TF-IDF is basically how often a term is used in the document versus how often it's used in the entire corpus of documents. And the idea here is if some word is used a lot, like the word the fact that it's used a lot in your document doesn't mean too much in the global scheme of things. But if you use a rare word, supercalifragilisticexpialidocious, that used to be, by the way, that used to be used in exactly one book, Mary Poppins. Now, I published a book with O'Reilly where I used this. Now it's used in 2 books. But if the word is used once in this book, it becomes highly, and nowhere else, it becomes highly relevant to that specific document. So that's what TF-IDF does. Let's see, ID to word 342. Oh, okay. We need to generate the corpus first. So, yeah. So the first one computes term frequencies across, and the second one takes our corpus that we have already built up and marks it up with TF-IDF. So now we are getting up to the point where some magic starts to happen. So at this point, everything we've done was largely janitorial. We've taken some text, we transformed it, we vectorized it, we cleaned it up. So the next thing we're going to do is we're going to build a latent semantic model. Latent semantic models are actually very interesting. It was sort of one of those really dumb ideas that actually happened to work. And the dumb part is not because it was created by dumb people. It was created actually by very smart people. But it's a dumb idea because it has no notion at all of what meaning is, and yet it starts to derive meaning. So what a latent semantic the theory behind latent semantic analysis is that you take, if you take 2 people talking about the same thing or a similar topic, they're going to largely use the same words. So your vector distance, so if you use similar words, you're going to have similar vectors. And if you compute the distance between those 2 vectors, you might get people talking about the same topic are going to be closer to each other than people talking about different topics. So that's the main, and there is a lot of math behind it. So we generated a model, and from there we're going to create a matrix index. So a word of word in here. This one is pretty quick, but it's actually a toy data set. So we only have 10,000. You have to do you might have to be parallel. If you're dealing with millions of documents or much longer documents, you might have to use some parallel computing. So that's may or may not work in your memory. By the way, so this guy has 16 gigs of RAM. I've never truly maxed out the RAM, despite the lack of trying. It's remarkable what you can get in laptops these days, and like I have not needed a Hadoop cluster in ages. Uh, so so the final so now we're going to uh, so I just wrote a very simple function here. Takes any piece of text, applies pre-processing, and then gets you 10 more similar sentences in the latent semantic model. So I don't know. Give me a piece of text that describes the movie or something.
Fast.
Fast and Furious is epic flick of motorized mayhem. Okay. Oh my God. Oh, not exaggerated enough to be a parody of growth. This is better than I thought. Yes, latent semantic analysis is fun. You get stuff out of it. Oh, towards the end, some all fears morphs into the mundane 70s disasters fleek. Well, maybe not. There is an epic here, but you have to put it together yourself. Yeah, none of them, by the way, have been too similar. So that's our top rating here. Oh, I'm gonna die here. So not. But here you start to get an idea. So now based on this corpus, if you want to put let's do actually something emotional. Trump is an angry beehive. Oh God. Yeah, I'm not going to read it. You read it yourself. Yeah. So you get an idea of how this is a lot of fun.
That last one's pretty good, actually.
Oh. Okay, for those who can't read, it's Upper West Side exercise in narcissism and self-congratulation disguised as a tribute.
Sounds like Woody Allen.
Well, yeah, I mean, but Trump is also from Upper West Side. How the hell did he? Oh, God. But you know, a lot of it is actually an exercise in garbage in, garbage out. So I happen to have an exceptionally fun corpus here. Yeah, whatever you train it on is what you're going to get. So, how are we doing on time, by the way? 12:15, right?
Yes.
Okay. So I'm actually going to switch gears. So LSI is fun, but I want to show you the second thing that the second things that I've built based on largely the same tools. So this is a tool based on NetworkX. So NetworkX is what NetworkX does is it basically keeps graphs of things. Things are word. Usually, it could be people, computers. So you can do vulnerability analysis on social networks. You can do centralities to look for most influential people, etc. I'm using it as more or less a straight-up graph database. And what I'm going to do is I'm going to build from a very similar idea of word similarity on vectors. I'm going to build a graph of words to concepts. So the input here, one of the inputs, I'm going to use the NRC lexicon, and then you can load your own text from the movie database as well. So so yeah, clean text. That's just some regular expression stuff. So what this discourse mapper is it's basically an encapsulation of the graph model. I'm going to throw some stuff in it, and then I'll show you what it's like on the inside. So I've already pre-vectorized the NRC data, the emotion lexicon, just so it's quicker to load. Uses the same linguist package to process and tokenize things. And the NRC lexicon has already has markup for anger, joy, etc. So emotions. This is the emotions I have right now. So this is really starting to approach the inside-out world. So we have anticipation, joy. Negative and positive are old school sentiment, just to compare. Sadness, disgust, anger, surprise, fear, and trust. And you can imagine that a lot of those things are going to be highly correlated with each other. Fear and surprise are actually highly correlated. They're kind of hard to tease apart. Trade. Yeah. So that just loads up all of the tokens that I pre-built, and I'm going to so discourse mapper graph.
You just mapped the sentiment, the emotion to the various words in the dictionary.
Yeah. So this dictionary was pre-built before I came here, and I'll post it up online as well. So if we look at words associated with joy, worship, victory, utopian, sterling, sound, scholarship, motherhood, nice words, anger. I really don't know why this came up. I think somebody was trying to get their Wi-Fi working. Unthinkable, gibberish, powerless. Why wireless? I don't get it. I don't get it. But in general, yeah, this sort of makes sense, right? So just from this, without loading any of the movie review data, we can start getting stuff. Actually, you know what? I'm going to switch to slides for a sec because there is a specific. I just wanted to show you what this looks like. So this graph here, that's actually a very shortened version of the emotion graph. So this only has 3 emotions, I think maybe about 1,500 or so words. So there are some words that are completely unambiguously attached to a specific emotion, and then there are words that are sort of neutral and they're attached to a number of different emotions. And what we're mostly interested in are those ones. So those end up being they end up being the marker ones. So now, how do we classify text physics? So we place a node for a specific piece of text here or an author. I actually I don't like looking at a specific piece of text. I like looking at authors, because the more text we have from a single author, the more accurate we get on their estimate of how an estimate of their sentiment. So we place a node for an author, and we start making links between this node and any marker words that that author has used. The other thing we can do is instead of emotions or instead of authors, we can start using domains. So in the election context, the two domains are Trump and Hillary. So we can model domains in terms of what words are being used in association with those domains. And now when I tweet about either Trump or Hillary, I can figure out, so I'm mentioning Hillary, but I'm using words that are associated with the Trump domain. Aha, I guess I'm a Trump voter. God forbid. What we're doing is, actually we're doing the same thing as we did in LSI. We're creating a vector, except in this case we're creating it in graph space, not in sort of flat vector space. We're creating a vector, and we're measuring distance between vectors. And the vectors here are either pieces of text or authors, and the other set of vectors is based on emotions. So when I pull out, so this is the vector associated with. This is the vector associated with anger. Now, so I'm going to actually try to do so predict let's see, Trump. I'm just going to go grab the first thing that. Okay. Let's see what the evangelical leaders think about Trump. Okay. 3 paragraphs of text. Okay. Unicode problems, haha. Don't you just love Python too? Yeah. Oh, it's. Yeah, it doesn't like the quotes. I know. Okay. Well, there's positive and there's some anticipation. Interesting. So while they're condemning, they're actually not condemning, or well, no. Okay, I see why it's happening here, because so first it actually describes the group. So I'm just going to take this quote here. Sorry? Okay. So, well,
I didn't see it in the code, but I assume you're doing like some negations, right? Like, so if they say it's not acceptable, that's getting.
No. So that's that. No, I'm actually not doing that, and that. So the solution to that, the negations are really terrible because there are so many rules. The solution to that is instead of taking single words, you take bigrams.
Right.
and it's a very
Some of the system you can mess with that too, like if something goes from unacceptable to
yeah.
or useless to use.
Yep.
Love your neighbors as yourself at the end of the phrase.
Yep. So yeah, this is one of the problems with doing sentiment analysis on larger chunks, because one of the interesting things is actually to map how emotions change during the course of a larger discourse. In fact, well, we have a debate coming up on Sunday. What I should do is I should rig this up and listen to the closed captioning in real time. That would be cool, because then you could actually map the emotional roller coasters as they're going through. That would be. I have an idea for a weekend project.
Is there a way to get the closed caption feed? Like,
Yes.
By API or something?
Yeah. So as far as I know, the debate will be broadcast on YouTube, and in real time. Yeah. So then the YouTube is going to have a closed caption feed that you can get from my API. Yeah. So. Yeah. Well, I'm keeping you all from lunch. So. Question to the organizer. So is there going to be a place to post code or to post stuff on GitHub?
I'm pretty sure.
Okay. Yeah. So I'm going to have everything available on GitHub, all of the code and all of the data. So you should be able to go and play with this. Yeah.
What's your GitHub username? In case it doesn't.
Okay, easy enough. And actually, some of the stuff is already there. So GitHub is yeah. So some of the stuff. The graph-based tools are already there, and I think there is also a set of slides. I published this actually as a library called Snow White, and you can pip install it. I need to make sure I haven't updated in a couple years, so I need to make sure that the package is still okay. But yeah, so all of this stuff is going to be available on. And yeah, I don't want to keep you from lunch any longer. Thank you very much.